Hi everyone and welcome to this presentation. My name is Corbinian and I will present our approach towards safe autonomous driving through a real-time safeguarding concept for motion planning. The key idea is an independent module, what we call the supervisor, that continuously verifies planned trajectories under strict timing constraints on automotive-grade hardware. I will start with the motivation, then explain the proposed architecture and implementation, and finally show our evaluation results. Autonomous driving functions belong to the most safety-critical systems in the vehicle. They directly affect longitudinal and lateral control and must therefore comply with the highest safety integrity level, ASIL-D, according to ISO 26262. However, these systems have become increasingly complex. Modern motion planning often relies on optimization pipelines or even end-to-end and machine learning-based approaches whose internal behavior cannot be fully verified using classical design time methods. This makes it extremely difficult to guarantee that each computed trajectory is safe under all conditions. To address this challenge, we introduce an independent supervisor, a safeguarding module that validates every trajectory before execution and ensures that new valid plans are introduced within defined timing bounds. It effectively provides a runtime safety envelope around the planner, enabling continuous monitoring and predictable system behavior. In the next part, I will briefly show how this concept connects to existing work in runtime monitoring and automotive safety standards. In the context of autonomous driving, several approaches exist to ensure functional safety. At the foundation, we have safety standards such as ISO 26262 and ISO 21448, which define structured processes for validation and certification. However, they assume deterministic and traceable architectures, no longer true for today's systems. To complement these standards, different verification strategies have emerged. Simulation-based testing enables scalable evaluation of critical scenarios, yet realism and reproducibility remain limited. Analytical safety concepts such as RSS or barrier certificates can provide formal guarantees but do not scale well to complex, high-dimensional planning systems. Online risk assessment improves situational awareness through probabilistic metrics but are lacking formal guarantees. More recently, online verification has been proposed as a runtime layer that checks trajectories before execution, enabling partial ASIL decomposition. However, existing frameworks mostly focus on functional correctness. They verify whether a trajectory is safe, but not whether it arrives in time. But for safety-critical real-time systems, both aspects are equally important. Therefore, our work extends the idea of online verification into a real-time safeguarding concept which explicitly monitors both the functional and temporal validity of motion planning algorithms. Our safeguarding architecture separates the main autonomous driving software from an independent certifiable safety layer. On the left, we have the regular AV software stack running on the high-performance computer. It contains perception, prediction, and motion planning, but operates on a non-certified software and hardware basis, optimized for flexibility and performance rather than determinism. On the right, the supervisor runs on the real-time unit, also called the safety island. It receives the planned trajectories and vehicle state information through a message bridge. This module executes independently of the main stack and evaluates every trajectory before it is passed to the actuators. So, while the left side focuses on intelligence and adaptability, the right side ensures predictable and verifiable behavior. Let's take a closer look at what happens inside the supervisor. The supervisor follows a simple but robust pipeline built on the real-time operating system of the RTU. After startup, the system configures its network interface through DHCP and initializes the DDS communication setup. It then enters a waiting phase for incoming trajectory messages. If no valid trajectory is received within a defined time limit, the supervisor immediately sends a verdict indicating a timeout, effectively enforcing the time safeguard. If a trajectory is received, it is evaluated across several layers of feasibility checks. These include kinematic feasibility, ensuring that the motion respects vehicle geometry and curvature limits; dynamic feasibility, verifying that accelerations stay within physically achievable bounds; and continuity, which ensures smooth transitions between consecutive trajectories without abrupt jumps. After evaluation, the supervisor issues a verdict back to the main system, either confirming the trajectory is safe or flagging it as invalid. This feedback closes the safeguarding loop and guarantees that only verified, timely trajectories can reach the control layer. For our current implementation, we selected the Zephyr real-time operating system running on an automotive-grade development platform based on the NXP S32 Z2. This hardware provides a heterogeneous architecture with separate high performance and real-time domains, making it well suited for safety-critical automotive workloads. To evaluate our concept, we first established an offline test setup rather than running the supervisor directly in the vehicle loop. Pre-recorded trajectories were loaded on the high-performance computer and transmitted to the supervisor, which then analyzed each trajectory and returned its verdict. This setup allowed us to focus purely on timing and functional behavior under controlled and repeatable conditions. It reproduces the full data flow between the planning stack and the safety island, but isolates it from any external influences. For the quantitative results, we compare the runtime behavior of the supervisor on the real-time unit, shown in blue, with a reference implementation on the high-performance computer, shown in black. We evaluated 800 trajectories of varying complexity. While the HPC version shows strong fluctuations and occasional latency peaks above 1.5 milliseconds, the ARM-based real-time implementation remains highly stable with minimal jitter and an almost constant runtime of around 1.1 milliseconds. Of course, the real-time board is slower on average than the HPC, but this is expected since the goal is not maximum computational speed. What matters in a safety-critical context is timing reliability. The system must behave predictably and deliver results within guaranteed timing bounds. This confirms that the real-time setup provides deterministic timing behavior, which is essential for certifiable safeguarding and online supervision. To verify that the stability holds under long-term operation, we repeated the experiment 3 times, each with 10,000 trajectories executed on the ARM board. The box plot shows that all runs exhibit nearly identical runtime distributions with very small variance and no critical outliers. The final figure illustrates the qualitative evaluation of our supervisor. We visualized all tested trajectories shown here in both curvilinear and Cartesian coordinates. Infeasible trajectories were automatically rejected and are displayed in gray, while the remaining feasible ones were assigned a cost based on their dynamic and geometric properties. This large-scale evaluation was not intended for online operation, but rather to stress the system by processing complete trajectory sets instead of a single optimal candidate. The experiment allowed us to assess the computational limits of the board and verify that the full evaluation process remains within real-time bounds. To conclude, we presented a first prototype of a real-time safeguarding framework for motion planning algorithms. The supervisor runs independently on an automotive-grade NXP S32 Z2 platform and verifies both functional and temporal properties of planned trajectories. Our experiments confirmed deterministic timing behavior and reliable feasibility checks, but the current implementation still operates in an offline test setup without integration into a closed-loop system or fallback functionality. So at this stage, the concept mainly demonstrates feasibility rather than completeness. Nevertheless, it provides a solid foundation for certifiable, real-time monitoring of complex planning modules that cannot be verified by classical means. For future work, we plan to integrate the supervisor directly into the ICVES stack, adding automated fallback handling for invalid or delayed trajectories, and conduct on-vehicle experiments on our research vehicle. These steps will bring us closer to our long-term goal, achieving safe and certifiable autonomous driving through real-time safeguarding. Lastly, I would like to thank my co-authors and the team at the Autonomous Vehicle Systems Lab for their collaboration, as well as ARM and NXP for providing hardware support and valuable technical feedback throughout the project. The code of our Supervisor framework is fully open source, so please feel free to check it out on GitHub. If you are interested in collaboration or want to learn more about our research, our lab's website is also linked here. That's it from our side. Thanks a lot for your attention.